Welcome back to Thermochemistry. We are on page 7, working example 1411. I hope you've tried this one at home. If so, let's see how you did. If not, let's see if I can give you a boost in the right direction. We have iron 3 oxide reacting with carbon monoxide, and the problem tells us we have negative 26.3 kilojoules. So that negative is a good indicator, or a perfect indicator, that this is an exothermic reaction. Now, as if that wasn't enough, the problem also says that heat is produced. And so again, we know that when heat is produced, we put it on the product side. So we would write that as plus 26.3 kilojoules of energy. And since it is exothermic, we know that the system released heat into the surroundings, which means that the temperature of our surroundings increases. So that gives us some indicator of what type of reaction we're dealing with. Now let's take a look at our dimensional analysis. We're given mass of carbon monoxide and we need to get to kilojoules. Our conversion factor is provided for us. It's this many kilojoules per 3 moles of CO2, for 2 moles of iron, for 3 moles of CO, and for 1 mole of iron 3 oxide. So I've got 3.40 grams right here as my original given, and that's of carbon monoxide. It's very important to label these as you go so you don't get lost on the way. I want to eliminate the grams, so if one's in the numerator, one's in the denominator, they cancel. And I want moles. Mass to moles, use molar mass. So I'd have 28.01 grams. And then make sure you keep the negative here, or you may neglect it at the end. I've done that more times than you can imagine. So it's this many kilojoules, but I must get the other part of my conversion factor from there. That's for every 3 moles of carbon monoxide that react. And if we've done our algebra properly, that should be minus 1.06 kilojoules of energy. Now, what that means is that the energy required to break bonds must be less than the energy released when bonds are formed. So in other words, we made more energy than we spent. You can kind of think of it as a business analogy if you want there. Now, let's take a look at this on a quick energy diagram. Not a cooling curve, mind you, an energy diagram. That means we put potential energy on the y-axis, and there's just some vague course of reaction. What this tells us is that our reactant potential energy is higher than our product. So, product, reactant to product, this is our delta H. So delta H is equal to minus 1.06 kilojoules. Now in the next unit, you'll see that this is not just a downhill slope here. You'll see that there really is a barrier. All we're showing are the differences in potential energy. We're taking a smaller value and we're subtracting a larger value, and so we get that negative or released amount of energy. Now, the next problem deals with the thermite reaction. And we need to talk Mr. Coder into doing this for us. We do it outside because it releases a tremendous amount of energy. Now, there might have been a typo in your notes. I know there was one negative that was a typo, and that might have been it. So check your notes very carefully, please. We have 25 grams of aluminum, and they react with iron 3 oxide. Now, the advantage of this single replacement reaction is that we form iron, and that's what was used to hold railroad ties together when they first expanded the railway out west. They would do this little thermite reaction over every joint or meetup space between the railway ties. Now, what this is it's an exothermic reaction. You are going to see that heat released when he does that demo for us. It's really cool. So that means we add the energy term to the product side because energy is produced as a product. Let's do our dimensional analysis. We start with aluminum. And we're assuming in this reaction that all of the aluminum would react. So I have 25.00 grams of aluminum. I want to get rid of grams and go to moles. Mass to moles use. Molar mass. I can't imagine that after a year you have to be so sick of that phrase. Mass to moles, use molar mass. Now, I want to eliminate the moles. So I put them opposite, and I want kilojoules, and this tells me I would get negative 849.0 kilojoules released for every 2 moles of aluminum. And when I do that mathematics, I get a negative 786.7 to 4 sig figs. That has 4, and this has 4 kilojoules released. That means the temperature of my surroundings will increase as the system pumps heat into it. So the system's going to send heat transfer over to the surroundings, and the temperature will go up. Now, what we're going to be doing next is looking at the types of equipment that is used to actually measure energy changes. And so it will be a little bit of a shift, and then we'll come back to some very similar types of mathematics. See you there.